Okay, hello everyone. Welcome back. This is my last day here for the summer school. Quick, but it was good. I hope you also liked it. I'm always. We still have a bit more to go. So I have to do 2 sessions today. So I will see if my voice will cope with that. In the previous sessions, we looked very much at the hardware level. We also do a bit on the hardware level today, but now we are moving more and more into a more abstract level. So the first session is about operating system virtualization, but that's only one title. For some reasons, I had to squeeze 2 lectures into one, so this is only the first title. In this lecture, we will do 2 things. We do not only virtualize operating system, or on an operating system level, but we also virtualize the network. Because the network resource is something, as we saw, or what we will see, is a quite important resource, especially for research work done today. So, what is operating system virtualization? It's actually a lightweight, or that's the marketing tag. It's a lightweight alternative to hardware virtualization. We will see why it's lightweight. Instead of virtualizing hardware, and by virtualizing hardware, we took a resource, for instance, the CPU, put a layer in between the CPU and everything that runs, the software that runs on top of the CPU, and made it work like, in a similar way, multitasking is working inside an operating system. So we shared a resource, a virtual resource, using, for instance, a virtual machine monitor, and therefore we, on the VM level, we had then virtual resources, which could be shared between different virtual machine, and all running on one physical resource, or on a set of physical resources. Operating system virtualization is not a new idea. As you can see, there it has some history. So if you have some background in Unix or BSD, you probably are aware of change root and BSD jails. So that I'm not happy with the term that this is actually virtualization. It was just, it constrained. So you used change root or BSD jails to constrain a program, to restrict it to a certain area of your operating system, so it could not see other things, and it could not do harm to other things. So it was typically used for running a web server. So if the web server has been hacked, the hacker has been trapped in the jail. So he cannot, or it was difficult for him to compromise the whole system. He was only able to compromise the small space the administrator gave him to run the web server. Slightly more sophisticated approaches were Virtuoso and OpenVZ, that were the first VMs that were commercially sold and commercially available. I'm not sure about here, but they were pretty famous in Europe and the US. So it was in the mid of the 2000s. You could have a virtual Linux server for very little money running. It was very similar to the cloud model, very, very similar. But it wasn't that advanced. So it was also kind of a compromise, because we will see it, to properly virtualize the resources, some work has to be done. And now we have Linux containers. We also have Windows containers, or we are almost there for Windows containers. There are plenty of flavors. LXD, LXC, Docker. I think Docker is the most popular one. There is Rocket, there is Singularity, there is Shifter, you name it. So there are plenty of flavors out there, but essentially they all use the same base technology. And in this section, I will stick to the Linux flavor. The Windows flavor is working in a similar way, but in a Windows way. So a traditional VM guest is a full operating system. It has a full stack, and on the lowest level, there is kind of an operating system which believes that it actually is running on hardware, and has its own view and own hardware. So it has its dedicated CPU, it has its dedicated memory, and it lays out how it uses the CPU and how it uses the virtual memory. And below that, we have either virtualized hardware or fully emulated hardware to make the operating system believe that everything is fine on the level below. The upside is you can run any operating system that supports the virtualized hardware or the emulated hardware. So you just look up your what your operating system requires and what driver support you have, and then you look at the emulator or at the virtualizer, what kind of hardware it supports and what kind of virtual hardware it actually provides, and then you can then it's quite straightforward that you know, okay, I can install this operating system in this kind of virtual machine environment or on this in this emulated environment. Containers are different. They share the operating system. They share the operating system kernel. So they don't come, a container does not come with its own operating system. So we just move one level up. Why? So if you share a machine resource, for instance, for research purposes, we will see it way more efficient. Why everyone should install its own operating system? It's expensive, and it comes with a lot of extra overhead. Because everyone has to bring its own operating system, and the operating system already occupies plenty of resources, even if your virtual machine does nothing. However, it's a bit less flexible. You stick with the operating system that is actually virtualized. It's the same way as with the emulated or virtualized hardware. If it's an Intel-based CPU, well, it's an Intel-based CPU. That's what you have. If you use a Linux container as an abstraction level for operating system abstraction, you stick to that Linux system. So you cannot run Windows on that. You could still run Windows, but then you have to install an emulator inside the container. That will work. We do that. But we can talk about this in the next session. And even what makes it even more complicated here in this case is you also share all hardware interfaces. So there is no emulated hardware. as we would have in a virtualized or an emulated system. So you use, the only option is either you are allowed to use the hardware that's on the host system or it's not. And that is decided by the virtualization platform. Because you share you share the kernel interface and or the whole operating system, which essentially includes all the drivers. And the drivers plus operating system, they control the user space access to any hardware resource. So if you rely on, say, a certain piece of hardware, let's say MPI hardware or GPUs or something else, it is required that not only the hardware is present in the machine, like physically present, but also that the operating system that is running the virtualization platform for Docker or actually has configured it in a way that it can be passed through, or that a tenant on top is able to use it. And then there is another downside, and that's why it took so long, because the idea is pretty old, to actually implement it in a way that it actually now, it really took off. I mean, you know, Docker is really popular, and it really took off in the recent years, but it took some time until it was properly implemented. So the implementation is complex, and it's still complex, and it's still not 100% there yet. We will briefly, I don't want to go in all the details with the implementation, but I will briefly show you why it is that complex. And I don't have a slide, but I will briefly talk about the security issues here. The key to all this is what we call namespaces. You probably know the term from programming languages. It has a similar way here. The namespace is kind of a tool to abstract the global resource. So it's a way to share operating system functionality and virtualize operating system resources. It's actually well, I spoil you a bit for the next session. It's actually, even though it's complex to implement, we will discuss this. It's the only ingredient you need. So all from the container list I showed before, and the list is even longer. It's not only Docker is not the only game in town. There are plenty of other implementations. They all build on the same technology. Anything else is just flavor, implementation details, making your life or trying to making your life more convenient. But in the very end, they all use this same simple technology, what we call namespaces. The main idea of containers is, well, there are two main ideas, is you take a process, that's the program, or a group of it, and create a subgroup. And this subgroup is isolated. So everything within the subgroup appears as you would run this process or this program on a freshly booted Linux system. You don't see anything else for now. That's the naive way, but you can imagine it like that. So and for each operating system, if you want to implement your own way of containers, say Windows containers, you have to identify all the system resources a program needs to run, create namespaces for it, and then virtualize them. And here we take a look at the Linux container implementation, and the most basic system resource an operating system provides is to create a process. That's the very, or the most important, the very basic functionality an operating system provides. It allows you to start a program. So that's why you start Windows in the first place. It gives you the option to run a program which actually does something for you. And the same applies for Linux. You start Linux, the operating system initializes the hardware in a way that everything is ready for you. And now you can start actually working. Start a browser, start an email client, or start a program that actually does something for you. The operating system is actually made to operate the machine. So, how does the namespace work? Every time the Linux operating system starts a program, it usually does two calls. There are some variants in between, but you have to think about they're just two calls. One is clone. It actually replicates the current process, and then it allocated a new process space. Then it runs exec, which actually replaces all the code with the new code, and then it runs the new code. So that's the very basic idea of starting a program. This is all hidden from you as an end user. You double click on something, and this happens. Or if you're a shell user, you run /run something. That's it. So if you do a container, this is the first place we need to hook into. At the very last moment the program starts, we need to restrict the access and the view to the rest of the system. That's the whole idea. And at this point, we decide what the program is able to do and what the program is able to see. There are some more API calls in that field, but I'll leave it at that. But this is what Docker does if you run a Docker. It does a lot of stuff in before. We will talk about this later. But in the end, you said, okay, the entry point to my Docker container is the following program. And this program is actually executed that way. Anything else is just, well, a convenience layer to make it easier or nicer for you. Once we have the program, we need to think about storage. Like, what is the program able to see? You want to partition somehow the way your newly created container is able to see what is on the system. What parts of the host system should be mapped into the container and therefore visible and usable, and what not? It's a very basic idea. It comes from the old change root system calls. This is when you boot a system. At some point, you have to say, okay, this is what I consider as root on a Linux system, which is the most leftward slash, and this is. And anything above that is visible to the system, and anything below that slash is not visible to the system. And yes, if you run Docker, if you're an experienced Docker user, you know you can map whatever you want, whatever is convenient, or the Docker host, if it's a commercial one or if it's a remote one, gives you options to map certain file system parts into it. Well, you can have shared subtrees and so on. So I skip with that. I skipped that a little bit. That's mostly technical, but you have to think. It's all about visibility of the file system, because you're not anymore alone in the system. That's the big difference to virtualization. Then we need, well, the implementation of this whole container thing. It took a long time. What was the version here? It's 2.419. 2.419 is pretty old. We are currently running, we just switched to Linux 5.0, so 2.4 was about, I don't know, late 2000s, something like that. So it's at least 10 years old. But it took time. It took a lot of time until the containers were there, and they're still not 100% completed, the groundwork, because it's operating system virtualization, so it has to be built into the operating system. So it's a feature of the operating system to provide this option. In the previous sessions, when we talked about virtual machines or emulators, they're usually not part of the operating system. They use it, so you run an operating system inside and you run an operating system outside, and typically the virtual machine monitor and the emulator are just programs. We discussed the complexity of them, but they're just programs. They run beside the operating system. This here is part of the operating system. So it's it's an integral or part of Linux. And because of that, the implementation is really complex, because you have to think what is all necessary to be virtualized. So you have to think about all possible ways of a program interacting with the operating system. So every operating system call has to be kind of virtualized, or at least we have to think about it. Or to put it in another way, every resource, like a CPU on the hardware virtualization, every resource an operating system provides has to be virtualized. So we have to put some layer in between, and to make it shareable between different tenants. So there was the UTS namespace, which was a really boring one. The interprocess communication namespace, that's for pipes. Mostly the very important namespace that took a long time, the PIP namespaces, that's the process namespaces. This allows you to change the process IDs in the container. So the process ID, so you can start a process inside a container which has the process ID 1. For some programs rely on this functionality, but outside the container, the real process ID is a different one. And then, of course, network namespaces. So you only have one physical network card built in the computer, or maybe a few, but it's a limited resource. It's managed by the operating system. So you need a way to assign IP addresses, make the routing work between the host system and the container, so that you're actually able to run say a web server inside the container. And sometimes the programs are demanding. So some network programs actually require a proper network device interface to run properly. So the container has to provide the option to create a virtual network interface inside the container, so to make that program happy. And now, this is 99% done or 100% done right now, but it's pretty recent. It's the user namespaces. That was one of the most complex parts. Imagine, well, you all know we have a kind of a privilege system. There are many users running on the same system, and there is one, or there are a few users which are more privileged. In Linux, it's root. It's called the root user. It usually has the ID 0, and it can do anything. That's the administrator account on Windows. That's the user account that actually can do a lot or anything on the system. It actually controls the system. Here, similar, some programs actually require you to run the program as root for technical reasons. It is very important for them because they require some privileges, and they check. So the source code, the program check when it is started. Am I root? Do I have user ID 0? If not, abort. Don't run. Just provide an error to the user. Even then, we have now isolation, and we could allow the whatever user ID to do whatever it wants in its own namespace. It wouldn't allow the program to run. So you would have to change the program. This is usually not a good idea, because changing a lot of programs just because you want to run them in the container is not a good option. Programmers don't like this. So what we need then is to have the ability to have different user IDs within the container, but actually the program is running on the whole system, so on the outside system. It just appears inside the container that it runs in its own separate space. So we need some mapping in between. So inside it runs as root, outside it's a regular user. Inside it has privileges, outside it hasn't. It does not have these privileges. And there is no real barrier in between. So this was a very technical and a very complex task, because you have to touch many places in the operating system code, and every place has to check: do I run inside the container? Do I run outside the container? What are my privileges inside the container? Okay, I can do things. What are my privileges outside of the container? Oh, I can't do that outside of the container. So, and every tiny mistake here might compromise the whole system. So it might introduce very complex, very hard to understanding security problems. The Linux code is or every operating system code, these are very complex systems consisting of a lot of lines and very complex code passes. So overviewing that, that's not an easy task. So the current implementation looks like that. Each process has the user's ID, or each process run by a user has two user IDs. One inside the container and one outside the container. And then there is a table to map in these. So a very simple example: user ID with the user with ID 1000 starts a Docker container or a Linux container with user namespaces enabled, and then it actually allows you to start a program or initialize a program inside the container with user ID 0. And there is another problem with containers. We now share the hardware and we share the operating system. Now, there is no more, because if we share the CPU, we can say, okay, the CPU had ticks with, let's say, 2 gigahertz. So we can say, okay, you get that many ticks per second, you get that many ticks per second, you get that many ticks per second. Even worse, now we share the memory. If you start a virtual machine, you know, if you start the VMware, you have to pre-assign. You say, okay, my Windows instance gets 2 gigabytes of the 4 installed on my laptop. Or my Linux instance gets 2 installed of 4 on my laptop. Now we share the memory. It's just a process, it's just a program. So the program can go crazy. So this is a very simple example how you can, so you can try this in the pool if you want. This will break the Linux system in a very short time. It's just a line of shellcode, it does nothing. It runs forever, while true. It creates a dir, it goes into that directory and does it again. It's not about the file system. The file system may also break at some point, but the file system will cope with it. But what you create is you create this directory entry record inside of the Linux virtual file system, which is restricted. And this memory is not simply reclaimable. So if you have no quotas implemented on the file system level, at some point you will run out of kernel memory. And this runs as quickly as this does not more or less nothing. It even doesn't, usually it doesn't touch the hard disk at all. So it runs it runs incredibly fast. So you will consume all the kernel memory within seconds, depending, of course, of the machine, how it's configured. So if you want to share resources on the container level, which might be a good idea if you want to share in a HPC setting or in a cloud setting, if you want to share like small-grained resources between multiple tenants, you have to be more careful. So container provide you some kind of isolation, so it provides you the option to isolate programs from each other. So if the Apache is hacked, it won't compromise your system that quickly. But if the user is bad, you have to be more careful. You have to actually implement proper resource control. That's the other complement of the container implementations. It's the control groups or C groups. They can do two things. They can protect you, but they can also provide you guarantees. So you can say, I have certain jobs run in certain containers, which I want to have a guaranteed quality of service. So I want to have that amount of CPU available to this. It doesn't mean that the resource is gone. If you start a VM, the memory is gone, because the operating system running in the guest operating system will take that memory and partition it and use it. So it's usually fixed, assigned, and it's gone. Here, it's more flexible. So, well, one of the most important resources you have on a computer is the CPU. So you can implement something that allows only a certain amount of CPU time for a certain process. As I said, it can go into both ways. You can guarantee a minimal CPU amount, you can set an upper level, and so on and so on. And the second important resource is the memory controller. So you can actually restrict how much memory a process can use. Now, one really important problem is still the security. The attack surface from inside the container is huge, because every potential operating system call has to be hardened in a way that you're not allowed to break out of the container. Because if you break out of the container, the whole machine is yours. It's way harder. Well, there are options, and there are always options, of course, to break out of a virtual machine, but breaking out of a virtual machine is much harder. Typically, the vector of breaking out of a virtual machine is either exploiting emulated hardware code, like one popular exploit was exploiting an emulated sound card or an emulated network card, because that is code that runs in context of the host machine. So you need to find a way to run code in context of the host machine. If you exploit your own machine, well, enjoy, have fun. It will just, in the worst case, or in the best case, it will crash. In the worst case, nothing will happen. So to break out of a virtual machine, you need to find a way that your code, or that the code you want to inject, runs in the virtual machine monitor and not inside of your virtual machine. If it runs in your virtual machine, nothing will happen. So emulated hardware is typically one good attack vector of breaking out of VMs. Breaking out of containers is way more simpler, in theory at least, because the attack vector is every interaction between whatever runs in your container and the operating system below can be used. And there are a lot of options to do that. Fortunately, well, it took some time, but fortunately it's mostly secure. Maybe if you read the news, I think 2 weeks ago or 3 weeks ago, there was another breakout option which has been fixed. But the risk of implementing a security problem inside of the container is way higher than the risk of when implementing a virtual machine monitor or an emulator. So one idea is, well, can we mix these two things? Can we have both? Virtualization and all the container features. And the very important question is, how expensive is that? You know, when you have a virtual machine, you have to boot it first. This takes a bit, depending on how fancy your system is, but it takes a bit. Even if you have a snapshot of the booted system, it still takes a bit, because it has to load, I don't know, 2 or 4 gigabytes of RAM, which you wrote to the disk, back into the RAM, and initialize everything. So it's still, if you pause the VMware, it still takes you, I don't know, 20 seconds maybe 5, maybe 10, depending on the speed of the system, but it still is a significant amount of time. When you start a container, the overhead of starting a container is almost zero. as we saw, the only thing what we have done to implement the container feature and to start a program inside the container was we added to the clone and exec call just append a few options. That is nothing. It's the same structure as you would, or the same code path, or almost the same code path as you would follow if you start a program not running in a container. So the overhead is significant. And the other thing is the memory overhead. If you start a program in the container, you will only lose as much memory as the program is currently actually using. And you can do a lot of memory management. So that maybe the program starts and uses a bit of memory, but after that the memory gets colder and colder. It's not used anymore because you always cycle in another code path, and then you can swap it out and can reuse your fast and expensive memory for other processes and other containers which really use it currently. So you're more flexible in running that. If you run a virtual machine, you waste a lot of memory just by booting the operating system, because the operating system uses a lot of memory for just initializing everything and keeping track of everything. There are now ways to do this more efficiently, especially if you know what kind of operating system is used and if you do the right tricks. So this is not very much up to date. This reflects about the world it has been roughly a year before from today. So there was the Clear Container Initiative. They implemented the KVM tool, which is a really lightweight virtualizer. It runs on top of the Linux operating system and uses the KVM implementation as a virtual machine monitor, and is made just to virtualize Linux, a very special Linux system. And this Linux system can boot more or less directly in less than 30 milliseconds. So they put a lot of effort to make that work. And then, so the startup time, they could improve that a lot because you don't need to initialize hardware, you don't need to do a lot of things, so you strip down everything and make it as efficient as possible just to run containers. And the other part was the memory consumption, and then there are some nice implementation hacks, I would say. One is the in-place execution. So if you have a SSD memory, you execute the program directly from the SSD memory because it's not as fast, but similarly fast. But what is currently more or less standard is the same page merging. So you have to imagine you run then multiple VMs, all running exactly the same Linux kernel. And because it's exactly the same Linux kernel, it uses exactly the same memory structures. And then you can share the memory pages of the Linux kernel, at least some of them. This can be done really efficiently. I'm not up to date with the current implementation, but it can be done really, really efficiently. So this is a way to secure the container if you want it to run inside of an insecure environment. Otherwise, containers require some degree of trust and some degree of cautions compared to VMs or emulators. So now I come to the second part of my lecture today, because I have 2 in 1, and afterwards another 2 in 1, because my last day. Another important resource we need to abstract is the network. We will see that there are many applications for that, but essentially to make research scalable and movable, especially in a seamless way, the network must move with it. And usually the networks looks like this one. So you have some switch or some hub in between, you have the cable in between, or you have the Wi-Fi infrastructure. It's also tied and mounted to the wall. So it's typically immovable. It belongs to the local infrastructure. But that's sometimes, if you want to abstract and if you want to make your research or your machines movable or portable, sometimes these are connected to machines. So they rely on services which are pre-configured. So you cannot simply take this machine and put it into another network and then hope for the best. For this simple Windows machine, that's all right. It uses DHCP, gets a new IP address, and hopefully all the services that are installed on the machine will continue work. If you do that for a web server, things are more complicated because it has an IP address and there is a cascade of other services in front of it doing load balancing and whatever and routing it to that machine. So if you move it, you have to make sure that all the infrastructure moves with it and the IP address is routed then to the other place. If you move your VM or your set of VMs from one place to the cloud, the problem is getting worse, because every time you start something in the cloud, you will probably get a new IP address, or you have to buy one from them, and so on and so on. Before we talk about this, because this is a mixed course as far as I know, just a very, very quick introduction into networking, computer science networking in 3 minutes. Promised, it's no more than that. Also, with networking, we decided networks are too complex. We split into layers. That's something makes it easier to reason about it. I will talk today. We only talk about these 3 layers because that's the important one. The physical one. Also, later in L1, it's the lowest layer, it's hardware-based. Very simple, it's copper. It's the cable. Then we have the second one, the data link layer. It's already digital, but it's only slightly above copper. It just controls how the current goes to the copper. So we have 2 components. The one is the link control. So we want to see if there is something going wrong on the wire. So we want to detect if there is noise or some other errors happening on the wire. And the other thing is we need a very basic addressing of the endpoints of the medium. So that's the medium access control. And then we have the highest layer. What we talk about today is the network link layer. That's something we can identify sender and receiver. So that we can actually say, okay, I want to send from this point to the other point. All others are not important for this section. And then there is a bit of terminology, because we will use this in the rest of this session. There's something as a port. A port is what you typically have on a switch or on a computer, something you can plug. It gives you an interface and the connection. Does with that data, that we don't care about that. If this is email or if this is something else, we don't care about it. What we only care about is there's a packet and that has to be transported from one host to another one. And then we have something like the switch or the hub, something what is here where you can plug in the cable. So if you want to construct a network, you need at least 2 computers, and the switch is the device that helps you to transfer data from one computer to the other one. So you plug a cable from one computer to the switch, and then you plug the other to the switch, and then the data can flow between these 2 computers. The switch usually works on layer 2, so it connects the machine on the link layer, and then you have the router, which is a layer 3 switch, which has a bit more intelligence, because it knows a bit more about the computers that are available in the network. So it can send a packet maybe over multiple hops from one computer to the other computer. I will do this only very quickly. One very famous protocol we all currently use, but it's not the only one. There have been others. This is the one which remained. Well, there is of course the other one, that's the Wi-Fi. Is Ethernet. And why are we looking at the Ethernet? It's very simple, very old protocol. So it does actually what I previously said. You have a bunch of computers, you have a switch in between, and then you connect them. Very similar, very simple. So when we talk about virtual networks, the first layer we can virtualize is the Ethernet layer. So the idea is we emulate the copper cable. We would have done Ethernet compliancy. That's very good, because all computers, or at least most of the computers, know how to talk Ethernet, how to use Ethernet. It's very simple to implement. Actually, do we have the frames here somewhere? No. But as you can imagine, it's from the 70s. It's very simple to implement. And our virtual Ethernet, our virtual distributed Ethernet, well, we can run it completely in the user space, so it's completely detached from the machine. How does this look like? For instance, we can run a virtual machine and another virtual machine, which we can connect via a switch, a virtual switch, and then we can connect this switch with a real switch. And with that, we can emulate what we saw here. The implementation is super simple. It's actually, if you go to GitHub and look up the VD2 code base, it's tiny. Because Ethernet is such a simple protocol. We only need 2 components. We need a switch, and we need a cable implementation. Yeah, and then you can do a lot of wiring, so you can implement as many machines as you want. And what we do with VDE is we build complex networks of emulated or virtualized computers. And for us, like we are more looking into the back, so we are trying to keep older code bases usable and or reliably usable, like an old web server to be used with an old browser, or an old database to be used with another web server, and so on. For these purposes, the virtual Ethernet is the best option, because we don't care about higher protocols. So if we connect, for instance, an old Apple OS, Macintosh 8 or 9 client with an old Linux or Windows server running whatever, a database application or whatever, we assume that in the original days, these machines were connected via Ethernet. And everything that happened on the higher levels, like if they use IP or the IP protocol, or even IPX or some other protocols, it's not our problem, because that is implemented in the operating system stack, and the operating system makes the choices that needs to be done to get the connection up and running. But that's good for the old days. That's also good for archival. That's good for preservation purposes. Today the world looks a bit more complicated, unfortunately. We have now the standard computing center network speed is 40 gigabits, maybe even 100 gigabits. It depends on your budget and the capability of dealing with these speeds. If we're talking about these speeds, this is something that is very hard to be done in software, because the time, you can do the numbers. I forgot to put this on the slide. The time you have to process a single packet on, let's put it on a 4 gigabit speed, that's just a few CPU cycles. And a few CPU cycles on your CPU is nothing, because you need at least a few CPU cycles to fetch the data and at least have it in memory. So and then you'd still need time to reason about it, what to do with the packet. Shall it go that way? Shall it go the other way? And so on. And you see, there was a development in there. In the 90s, everything was so the only physical layer was the cable, and everything else was the software. So I spent a lot of time implementing and configuring a Linux router for my home network. It was all done in software, and even in computing centers, it was mostly software. There were some semi-intelligent switches, and some routers they could do a bit. They had some hardware tables, but more or less nothing, just software. Then with time, well, the speed increases and the software couldn't cope, especially not the general purpose CPUs. They were made for, I don't know, general purpose tasks, but not specifically to deal with network packets. So if you want to have a faster speed, you need to go put more and more into hardware. And we will do this a bit more in detail. So this was how the old Unix routers and the old internet looked like. You had the Unix servers in between, and they were switching packets more and more in software. But with the new and faster link, software couldn't keep up with the wire speed and the routing, and making all the routing decisions on the internet. That has been previously done in software. That's impossible today to do that in software. It's more or less impossible. And then in the 90s we had these ASICs. We could do, or we could implement simple or more or less simple algorithms quickly and efficiently in hardware, so that the hardware got more intelligent. It could do more and more things autonomously in hardware. For instance, we could do routing on hardware, we can do header modifications in hardware, something like that. Oh, that's, I need to show this. That's the remote listener code. I think you have to enter this number 1608 into the chat, if I know correctly. And then, well, we had now the hardware, and the hardware could do the routing, and everything was fast. But, well, as always, people demanded more. We need more flexibility on layer 3. We need quality of service. We wanted packet filtering, virtual LANs, and complex control, which made what we call switch OS. So we more or less implemented an operating system in the switch to have programmable rules. So we say, okay, we want to block torrent, or we want to group this set of IPs into a virtual network and route it that way, and the other group of IPs should be routed that way. So this is how it basically looks, what such a complex new style switch does. It makes decisions. Typically it has two routes. It receives a packet and then it decides either this packet needs to be modified or it needs to be forwarded, or both. And there is another problem. The internet and the fathers of the internet designed the network also on the lower layer to be autonomously as much as possible. If you switch, or if you connect this computer with that switch, there is a control layer that actually works things out for you. The switch learns automatically that this computer has a certain MAC address. That's not the IP address, it's the hardware address, because you have multiple ports, so multiple computers are connected to that switch, and it knows, or it tries to learn, on which physical port the packet has to be emitted. Because otherwise, yeah, you would have network collisions, or everything would be rather inefficient. That works in very small networks, but not in large ones. And then we have layer 3 control, that's routing. That's an even more sophisticated autonomous system. So I have, well, more or less, the internet is a complex web of multiple points which interconnect zillions of computers. So we need to determine And this is not about web addresses, it's just if you have this IP address and you want a way to another IP address, which is not in your local network, someone has to find a way to it. And this means that I can connect with my computer here, with a local IP address I get from your network here, to my computer or to a server in Freiburg. And that's kind of a difficult task, because if you do this by a car or by even by plane, you need routing. You need navigation. You need to know where to turn left and where to turn right to get to that point. And the designers of the internet, they invented what we called autonomous systems. This is a system, it's a black box, it's a router you can buy, and it implements a few protocols. And these protocols figure out what are my neighbors, and they fill automatically some databases, and at some point there is a global view on the network. So we know, or these systems automatically determine, because they talk to each other, how to go from here to there, even if we don't have a direct link with each other. That's pretty amazing. So there are plenty of protocols doing that. This is not very important for us. The important thing is that both of these layers come with a complexity, and they are designed to run in an autonomous way. That's the important point. Now we have something different. We have something else. We have what we call a modern data center. So you have these racks, and in a modern data center, you can have 100,000 physical machines. Each physical machine is capable of running 10 to 20 VMs. That's, let's say, Amazon or Google Cloud style computing center. So we have it in just one single place, about 1 million of interconnected hosts doing whatever they do. So the whole Instagram infrastructure is hosted in such computing centers, doing a lot of connections simultaneously. And then we have different traffic flows. We have what we call east-west. That's something that happens inside the data center. So you have some racks which just contain storage nodes, some racks which contain compute nodes, and so on and so on. And then we have the north-south. That's something that goes out into the real world. So, if you remember, we had these autonomous systems. They were designed in a world where you had a few hosts here and a few hosts there, mostly universities running a handful of services, maybe their website, a bit of mail, and that was it. Now you have all this layer 2 and layer 3 protocols doing a lot of traffic inside the data center, which is actually useless because it's a fixed infrastructure. You know what is there, you know your inventory. So there is no benefit of the whole protocol overhead for the east-west traffic, because you have a different topology and you have different requirements. You want to have the bandwidth and especially the CPU power for the switches for other tasks, getting the Instagram stuff out, or connecting Facebook users, and that's still pretty amazing, how fast Google is producing a search result from a huge amount of data. you cannot waste this time for, I don't know, finding out your neighbors and finding information about your neighbors in the computing center, because everyone knows what is inside there. So we have now this complete conflicting views of something that has been designed to be autonomously run without direct modifications. So otherwise, we would have to host every week a conference of all system administrators running the internet and then deciding what is the best route from here to Germany. And we have these huge data centers which cluster a huge amount of individual machines into a single room. And then we have to make things even more complicated. We invented the cloud. So we have something what we call multi-tenancy. Multiple tenants are hosted in the same physical place. So there is no proper network separation. And every one of these tenants comes with its own requirements. If Amazon, the Amazon cloud, the Google cloud sublets parts of its infrastructure to Facebook or to Instagram or to GitLab or who else is using that infrastructure, they come with very specific requirements to get everything connected, otherwise it won't work. At least not in a scalable way, because otherwise you have to send your admins there and they have to reconfigure everything, that everything is working. So just a very simple example. We will talk about the VM migration in the second session a bit more, or about migration scenario. This is only about networks. To migrate a VM from one physical server to the other one, that takes a few minutes. Depending on the network speed, how fast can you transfer all the data from one machine to the other one? Minutes. Maybe even seconds. But when it comes to the network, things are more complicated, unfortunately. If you have the top of the rack switch and even the outer switch, that's not something that can easily be automated. Someone has to reconfigure it. Or you have to wait for the autonomous system to reconsider, oh, I have this machine now here. Ah, okay, I learned this and I propagated this in my table and then I propagated it to the switches below. And while this migration may take minutes, the other may take days, either because someone has to work on the ticket and fixes the configuration manually, or you have to wait until the system and the protocols have consolidated and have learned that you actually did that move. And if this happens often, this won't work. So, even though, the main motivation for implementing software-defined networks is when you know your topology and you have a fixed infrastructure. And the main idea is to reduce the control plane overhead. So to reduce the way that is necessary to reconfigure everything. Because this is kind of a top-down approach. The internet was a bottom-up. If you do the top-down, and if you know the infrastructure, you can reprogram everything by just reloading the router hardware. Can someone please? Thank you. I almost forgot. So the main idea is automation. Still do a very quick how this looks like and what are the terms, and then I will spare you with most of the technical details. So a modern switch has three planes, what we call. One is the data plane. That is the part of the software or the hardware that deals with the packet transmission. There's a forwarding table, and it moves one packet to another one. And in the forwarding table, so for every packet that comes in, it looks up. Do I know this packet? If I have it in the table, I'll look up what is the right port to move that packet to, and then I will send it away. And then I have the control plane. This is the part which controls this table. Every time an unknown packet comes, I need to make a decision, or someone has to make the decision, and I have to update the forwarding table. And then we have the management plane. That is something that interacts either with other switches or with the user. So, what is the most, or how can we define a really or a software-defined network, especially in that term compared to the Ethernet? That's also a virtual network, but this is the software-defined network. It's an abstraction of the network state. You have, or you need to have, the global view in one place. It does mostly forwarding. It's not nothing really interesting what it does. It just takes a packet, moves it from one place to another one. And this regardless of the physical infrastructure below. And it represents a configuration state. So it captures a state or an abstract description of your network calls, your resources, your policies, and so on and so on. And as we developed operating system and diversified, we do this the same with the network infrastructure. So we implement certain tasks without knowing about the physical infrastructure below. And yeah, essentially decoupling a service from a physical device. So how does a software-defined network works in general? So we have three basic components. We have the devices, we have the controllers, and we have the applications. The SDN devices are mostly simply stupid devices that they just do forwarding. Data is represented as a flow. Every flow, it's unidirectional, directional, so a bidirectional connection between, say, if you connect to a web server, that is at least represented by at least two different flows. And then also the endpoint are abstracted, so it can be IP addresses, it can be tunnels. Yeah, it's implementation dependent. And the definition of the flow, that's kind of complex, because that has been done previously in software. So it's a complex decision, so you need to decide this packet wants to run from to go from this place to the other place, and to make the decision how this should be forwarded, that's a complex decision, and that requires to look up. Remember, the software-defined network has the global view of everything that is contained inside, or that is visible inside the network. It has to look up how to do that. And this is typically a complex operation. It requires a database lookup or whatever. The controller part, that's the main abstraction layer. That presents the global view, or that has the global view of the network. It knows everything about the network and allows the devices to to define the slows. And for that, you require typically a high-performance computer, because that is your bottleneck. Again, the internet was designed to remove all the bottlenecks because it was a distributed system. Now we create intentionally a huge bottleneck by implementing a controller which has the global network view, and everything is based on this controller. And then we have the applications. That's a very quick one. These are not applications like a web browser, or that's what we have on the level 7 of the network, but these are applications which implement policies, network overlays, complex routing decisions or something, access control, for instance. And one standard to control all this is the OpenFlow protocol, which is a lot to read. We have a full lecture about this. But this is not that important for us right now. Yeah, and some a bit more details about the SDN devices, because these are the interesting one. You have an API which communicates with the controller. You have the layer where the flow tables are, and you have the packet processing. And typically, there are two ways to implement that. As you can imagine, you can have it in hardware, or you can have it in software. Typically, you have something in between, because the packet processing as well as the flow table lookups are rather simple to implement and can be done in hardware really efficiently. Here, so some numbers. A software switch can be done on a box like that. It requires a high-performance CPU, but even if you optimize a lot, you can probably are not able to run more than 10 gigabits of it. So typically, you have a hardware part in it. A bit more about the flow tables. The flow tables are, as the name says, a very simple table. They have fields or matched elements, or elements that need to match. This is typically found in every packet-based firewall works that way. So it matches packet fields, and then it matches an action, like drop, forward, consume, like forward the packet to the controller, and so on. So it's a very simple implementation, and these are not very complex devices, but they need to be super fast. This is a schema how a typical controller looks like. So you have the northbound API that is something that connects to the outside world via API to control it, and you have the southbound API, which is standardized, which operates the SDN devices. So I skip this. I just wanted to, my finishing point for this network resource abstraction. There are many ways to do that. We started with the virtual Ethernet, and we can hypervisor-based overlays. That's something. You have the physical network which remains intact, and then you have hypervisors or virtual machines that interconnect with each other. An old but still very effective way of having a software-defined network is tunneling. So what you do is you put an Ethernet frame or a MAC inside an IP, move it along, unpack it again, and run the stack upward again. That's pretty much very simple to the Ethernet application. It's typically used to reduce the problem of MAC explosions in large data centers. So you package it and move it forward. And then you have the tunnels, like virtual tunnel endpoints. So you have different endpoints which know each other. The network or the transport way between the different tunnel endpoints are arbitrary, so you don't know what it is, and then you just move networks from one place to another. So that was the resource abstraction. It was a bit dull because networking is very complex, and squeezing this complex topic into 45 minutes is pretty hard, I have to say. I hope you still have a bit the overview why it works and why we need it. And in the next session in 30 minutes, we will put everything together, and it will be a bit more colorful, I promise. And then we take a look how we can make all this abstraction of machines and computer systems work for us in a preservation perspective and in the research data management perspective. Well, thank you very much, and see you in 30 minutes. Research. Develop local, deploy it, scale it, run it fast. Pause jobs, move jobs as needed. One way to achieve that is live migration, and then we will use the ideas of live migration for archival. But first we take a look about the options we have for live migration. We start with migrating VM. That's heavy. We migrate a whole computer, an operating system, and everything with it. So it's not an easy one. One way to make this happen, or the first, was to narrow the interface between the operating system and the virtual machine monitor. So to minimize the dependencies. Because after all, if we migrate it from one machine to the other machine, nothing has to be left. No dependencies on the original host. And we want to preserve the whole state, including network connection. Everything that has been running on the old machine should run flawlessly on the new machine. Of course, we want to minimize the downtime. People should notice that we actually migrated the machine because of whatever reasons, because the demand was increasing, so we needed to move it to another machine which is more powerful, and ideally no one should notice. And also we need to consider the total migration time and the cost, because it's not only the time that matters, that is the downtime. So that's what the end user is noticing, because the streaming server is down, or the service is down, or it's not responding quickly for that time. We also need to consider the whole migration time, because during migration we double the cost, because we use at least twice the infrastructure we actually used before, or we actually need, because we need the old infrastructure up and running, and we need the new infrastructure up and running, and something in between. So also the total cost matters for this process. And what are the main applications? So highly interactive services, everything that you don't want the user notice the downtime if you shift something forth and back. But also if your scientific compute job already passed a certain amount of time, and you don't want to waste that time because you already spent some CPU time, which might be expensive, to get it to a certain degree, but you haven't finished, and if you break it or if you stop it right now, everything will be lost. So you either migrate or you snapshot it. One thing is migrating network connections. So we saw this is possible if we were cautious and we made the infrastructure aware that we want to migrate it. If you implemented it in the right way, we have some mechanisms using, for instance, SDN, as we previously saw, to make that happen. So the network protocol state and IP address need to be carried over. There is a bit more to do. I skipped some nasty bits that needs to be done, but actually it's doable. And if you have a programmable software-defined network, well, it's there. For storage migration, it's good that, or it's necessary that you have the storage off the machine already. So you already use storage that is not physically connected or physically part of the machine, but it's network attached storage or some storage service already connected with the compute machine or with the machine you want to migrate. The tricky part is the memory migration. Memory migration is the state, the running state of the system. That is what is in the RAM or in the compute memory. It's not on the disk. It cannot be. It's not permanent. It's always in use. It's what we call hot memory. It's always in use. You cannot. You cannot. Or we will see. It's hard to identify parts which are not in use and which can be easily migrated, and parts that need to be they can only be migrated if the program stops running. Because as long as the program is running, it will modify the memory. Even if it's a very simple process, it will constantly modify the memory. We can in a basic theory, we can have 3 phases for the memory migration. We have the push phase. So the host to be migrated actively pushes its memory to another host. Copy it. We have the stop and copy phase. That's something we need to stop the VM, copy it, done. And we have the pull phase. So we have migrated the VM, but not the whole memory is there, and then it pulls memory afterwards. The trivial part of migration is the stop and copy phase. We stop the machine, copy it over, let it run again. This will, as you can assume, it will cost you something because it will take time to do so. So let's assume you have a medium-sized machine, say 16 gigabytes of RAM. Even if you have a fast network, copying 16 gigabytes of RAM to another machine takes a bit, even though the network is fast. And then you still have the overhead of rerunning the machine. So you have to initialize the memory appropriately, and then you load the memory, and then you can start it. So the pure stop and copy phase, that's the trivial one. It's simple, but it's not the efficient. So in real world applications, we have always a mixture of either pushing or pull phase together with the stop and copy phase. How does it work? I mean, I already told it, stop it, copy all the memory, start a new VM. It's simple, but you have downtime, and if you do live services, all the clients will break. They will notice that the machine is gone. It depends on the service, and it depends on the protocol, how tolerant it is, until the client is unhappy with the state of the remote part, and the client will give you an error and say, okay, server is gone, sorry about that. So we need to be better than that. Make it more, I mean, we are computer scientists and engineers, and an engineer tries to solve a problem if there is a technical problem. So a short stop and copy phase is always necessary. It's essential to copy the kernel or copy the hot part of the machine. That's what actually drives the machine, and that's mostly the operating system. It's difficult to imagine to have a live migration without stopping and have both machines in sync. That's difficult because that would require quantum computing or something, that you have exactly the same state at the same time in 2 different places. actually impossible, because both machines do something. They evolve, even if they just count the ticks of the CPUs. They do something. So the idea is, or very simple idea is, we start a new VM, and then we pull the memory pages on first use. So we use something that also the operating systems use. We page fault if the memory is not in the hot memory, if it's not in the fast memory. We will produce a page fault, and then we look for it. We will find it somewhere, maybe on the disk, and in this case on the other machine. It works. We can do this that way. So we have, however, a considerably long total migration time, because we have to wait until the memory faults, and then we transfer it, and then at some point the machines settle. We have, of course, a reduced performance during this migration process. Here it calls after migration, so after actually the second machine has been started, because every page will fault, every memory access will fault. We need to go into a special mode, look for them, where is this page, or where is this specific part of the memory? Oh, it's on the other machine, so we will have to fetch it. Even on the fast network, it's not that much. One page is not big, it's 64 kilobytes. That's not a lot, but you still have the latency, and that's by magnitude slower than if it's really close in a physical machine as a hardware. And the total costs are pretty high, because the dependence on the original host is there. We need to keep the other machine running for a significant time, and this is costly, and sometimes the whole point of migration is, or migrating the one machine to the other machine is, well, to make room on another host, because we need to repair it, or we need to fix it, or we need it for other purposes or something. So there is another idea which could be quicker. So we pre-copy stuff. We try to keep as much as memory as possible in before we start the second machine, and then we try to reduce the stop and copy phase by identifying what we call the writable working set. So essentially, we copy the full memory first, or almost everything, and during this copy process, that takes some time. Let's say 1 minute. During this minute, the original machine is still working. It does something. Even if it does more or less not that much, it does something. So it still changes memory. So what we do is we try to identify the memory that has been changed during that phase and copy it again. And we try to reduce the amount of the memory that has been changed, and after some time we hope that it consolidates. It converges to a small set that's the writable working set, and this is the thing we can only do offline. So we stop it, copy the last bits, and then we start it again. So recopying these dirty pages, so that's the technical word for a page that has been modified after so the clean pages are all that we have copied, they're genuine, they're clean. And then someone comes and changes something, these are the dirty pages. That still creates some overhead, hopefully that overhead is small, and due to the iterative copy, we try to converge it. One very interesting computer science question is when to stop iterating this. So we do it once, we do it twice, we do it a few times, and at some point we hope that we are quick enough, because certain pages are only dirtied or are only used in certain time periods because something happens. So after some point, the memory we copy from one machine to the other is getting smaller and smaller, so we are quicker and quicker. So every iteration we do takes less amount of time. And we hope that we get more and more clean pages back there, and less pages are dirted during that process. But of course, not all pages will be, that will be not the case for all pages. So one philosophic or computer science question would be, when to stop iterating, copying the remaining pages, and accept it, that we have to stop the machine, accept the downtime, move it, and start from scratch. And how to approximate that? It's very difficult, because it depends very much on the application, as you can imagine. This is a time series for tracking a writable working set for a spec, a benchmark. The benchmark uses, I don't know, different programs and does different computational tasks, and they used it also for estimating the writable working set. And you can see, depending on the program, the number of pages on the y-axis differs a lot. So in between Eon, I don't know what it actually does. That uses almost, that we almost have zero pages there. gzip, as you can imagine, because it touches a lot of memory, has a lot of dirty pages because it pulls the whole data through the memory. If you unzip a data set, the complete data set will be pulled through the memory. And of course, during that process, the writable working set will be rather large. So it depends very much on the application. It's very hard to put in advance. The second thing is the total downtime estimation. We have something what we call the diminishing returns, because for each iteration, the working set isn't reduced a lot, and the more we do, the less we gain. So the idea is to have a lower bound for the best possible downtime for a particular workflow, and the bandwidth. The other part is the bandwidth. Just a second. Sorry. The more you use the network, and the faster your network is, the faster, the less time it takes to transfer the whole memory. So you have a kind of a trade-off between service degradation and the total downtime. And the service degradation comes if you use all the bandwidth you have on that machine or between the two machines for migration purposes. You don't gain that much because the service is unusable, because all the bandwidth goes into the copying of the machine. Oh, I'm sorry. And you don't earn or gain that much for a lower downtime. In theory, the downtime will be pretty low. but the service quality will be bad. Or you use a lower bandwidth, so you don't use up all the bandwidth for the migration, but you have a longer stop and copy phase. So something. One option you have is you use the same trick as we did with virtualization. You use a virtualized driver. So you let the machine know that it actually is migrated. Make the machine aware that it is migrated. So what we call process stunning. So we have a service on the machine installed, which is able to monitor and stop individual processes. So we can stop or freeze certain processes, stop them dirtying the cache or dirtying the memory, and make sure that this is fast. This is typically a good solution for the practical scenarios. However, it requires modification of the operating system. So if the operating system is not supporting this, you stick with the old problem. So this is an example. I try to explain it. It's pretty. I also have to sit. I can't read it otherwise. The graphics is rather complex. What you have on the x-axis is the elapsed time. Total migration time is 71 seconds, roughly a minute. What this is it also runs a benchmark. It's a live migration of a web benchmark. We have 350 clients connected and 90% load of the machine. So the machine is under pretty much stress using network connections. So there are networking clients accessing a web server constantly, requesting that. That's a typical scenario you might have, say, for a Facebook server or something. So there's permanent stress on it, and it's typically fully loaded compared to the resources it requires. So in the first phase, that's the first part, that's flat. We copy the memory iteratively with a relative low bandwidth. So the total machine has a gigabyte, has 800 megabyte RAMs of RAM. So we start copying the RAM or the memory that is rather cold. That uses up most of the time with a very reduced bandwidth. In total, in this example, about 700 megabytes were transferred in 54 seconds. The 54 seconds of the 70 seconds. And from there on, the bandwidth is increased significantly to copy the rest of it. In total data was transferred 960 megabytes. That's about a factor of 1.2, so 20% overhead. So we copied 20% of the memory uselessly. But the total downtime was 210 milliseconds, which is good or very good, I guess, for a web server. So a typical latency of a web server for 200 milliseconds, that's not super fast, but it's acceptable. And it won't break applications relying on that service. So the service is just shortly blocking, about 200 milliseconds, that's not much, but it's back. Something more interesting, a migration of a Quake 3 server. So it's an online multi-game player. If you're multi-shooter aware listener here, you know latency is everything. The migration of the Quake server, it was a small one, so it has 6 clients. It had 6 clients and 64, only 64 megabytes of RAM. So Quake is a quite old shooter. Took about 7 seconds, and the total downtime was 60 milliseconds. So that's almost not perceptible for the players. So that's quite nice. And the overhead was 1.37, so it's 40% overhead. Still, but for such a small VM, it seems acceptable. Of course, today this is kind of a very small VM, 64 megabytes of RAM. That's really old. But you see, I chose these examples to give you an impression what can be done. The next thing is the container migration. It's not that heavy anymore, so you just move the inventory. You don't move the whole house. And what we had with the operating system virtualization, we already decoupled a lot. So we already virtualized the network in a way more, or in a way deeper than we have it with the VM. Because in the VM we still have a physical, or the operating system believes it still has a physical connection, and it has physical hardware using MAC addresses and all that. Here we just have mostly user space networking. So what a process usually just opens a socket, a network socket. So this is way different than from the network layer than on a virtual machine layer. So it should be simpler. So because everything is on a system call level. The other thing is we have a way reduced overhead compared to the VM. Because for the VM, migrating a VM, we had this problem with the memory. If the VM is configured to have 2 gigabytes, it's very hard from an outside viewer to decide which of these 2 gigabytes are actually in use. The old VM had 2 gigabytes, and we need to copy over the whole 2 gigabytes as they are, even though they are not in use by a program currently, or yeah. So that's why we did all these extra steps with the stop and copy and the push and the pull to identify which is actually in use. But still, we have to copy it because we don't know what is in that memory, and if it's just random noise, or if it actually there is some data written by some program at some point, that has been written by some program at some point. So the container-based migration offers a lot of improvements in that case, because we only copy the pages that are actually in use by the container. And since this happens all on the operating system level, we know, because the operating system knows. So how can this be done? Checkpointing and restore. That's a very old concept. It comes from old computers where you had to share very expensive resources, and so what you did is you put in some checkpoints that were defined points where you actually could say, okay, this is a point where I can resume computation in a later stage. This is a point where I can safely switch off the machine. Also for computer games is similar. So if you reach a certain checkpoint, you can continue from that checkpoint, and you don't have to start over from the beginning. The same idea, we can use the same idea for container migration, but slightly different. Because the program doesn't know that it is migrated. The program shouldn't take note of it. So the idea is we freeze the application. Like, let's say to the operating system, please stop this application quickly. Don't schedule it for a moment, that it does not run again. Dump everything we have. Dump the whole memory of the application and the whole state of the application to the disk. Copy it and unfreeze it after that time. We don't have the problem with the writable work set, because we can say to the operating system, please don't let this program run for a few seconds. But there are other nice applications for that. So debugging, load balancing. We use it also for freezing emulators. So we can talk about this in a later stage. So how does it work? First, we analyze everything. We retrieve the information from the operating system, like, let us know what files has this process open. That's very important. We need to know, because these files have to exist on the other machine then. What memory is in use? There been specifically memory, have some files been memory mapped, or some other memory tricks? Are there child processes? Are there threads running, and so on? Then we inject a bit of code into the process to get a bit more information. So we need to know the state of the memory, has been memory marked for certain tasks. We need credentials. We need to know what is the user ID, what are certain things. And afterwards, we remove the injected code. That's what the programmers call it parasite code. So Cryo works like a parasite. It infects the program because it needs to gather the state of the program from the outside. That's the operating system view. That's what the operating system knows about the program, but also a bit of the inside, to know what is the program currently doing and what is it seeing. And then if we restart it, we remove the injected code again. And the program is as it has been before. Yeah, the restore phase is pretty trivial. So we read the image file, so we have written everything to the disk or to some other place and copied it. So we read it again. We build the process tree. Timers are a specific story, I can tell you. Restoring the timers is pretty hard. It's harder than we actually thought. We do a lot of experiments with Cryo. If you have a machine that runs for a while and migrate the process to a newly booted machine, even though the time is synchronized between the two machines, there is another clock the operating system used that is monotonic. It counts something from the start to now, from the start of the machine to now, because it does not trust the wall clock. Because the wall clock can change. You can change the time of the system during runtime. That's no big deal. But the system relies, timing is important because you have timeouts, because you wait for network traffic. So you wait for 500 milliseconds. If nothing happens, you let something else, or do something else. And if all the timing just changes, everything will break. You will wait forever for something to time out, because the network is not working, and similar things. You rebuild the memory from the execution process. And then for that, you can also do the same trick. You run a page server and transfer the memory in a live mode, or you have the memory completely dumped to the disk and copy it over. Here written, so you have the cold migration, stop and copy it. And you have the live migration, which does a similar thing. Because if you do a live migration of a service, of a process, and you don't want the process to be stopped, like really stopped, you still have the same problem with the VMs. You still have to maintain a synchronous state in two different places. So you do a very similar iterative approach with some pre-dump and some stop and copy phase, as we have done with the VMs. And here is the comparison. KVM is a hypervisor. KVM is a virtual machine. And LXC is a container version. On the x-axis, you see the domain size in gigabytes. That means how large is the VM that to be migrated. And you can on the y-axis you have the time. And as you probably, or it's pretty intuitive that for the KVM, with a growing domain size, a growing VM size, the time grows, because you have to copy everything, even if it's not used. If you use the container, it doesn't matter how large the VM is. It only depends on the process. So if the same web server is installed on a tiny VM with only 250 megabytes of RAM, it takes the same time as you would copy, as you would migrate the same web server on a machine that has 4 gigabytes of RAM. But if you do that with a virtual machine, well, you have to copy the 4 gigabytes. Here you just copy the pages that the Apache is currently using, or the web server is currently using. And that is, given that it's the same process, that should be constant. So these are the migration. Now we did everything, abstracted the computer systems to make it portable, to deploy into different compute facilities and so on and so on. Now we have to think about the long term. This is my research domain, and that's why I'm doing all this research about abstraction of computer systems. Science in a digital age. Science is based on accessible facts, reproducible arguments and methods, and reproducible results. That's not something new, I can tell, but it changes. And citation is one of the most important tools we have as the researchers. Because here, that's this nice picture. We all stand on the shoulders of giants. Because we can work, we don't have to invent the wheel every time, but we cite that someone invented it and now I can build a car and do something more complex. And the same applies for your PhD. You don't have to do everything again. You have an idea, and everything else is you can find in the library or memory institutions, which keep track of it. And you have your tiny idea and put something on top of it. And that is usually tiny because how much time do you have for a PhD here? 3 years, 5 years, something that 4 years, yes. So that's not a lot of time. But this allows you to focus on one tiny aspect. And everything else is citation. You trace your research back to the beginning, Adam and Eve, or whatever you believe. Back to the beginning, back to Newton, and from there on you have a reproducible chain of arguments which you can make. Now things are different. We invented new devices, machinery. First, we started digitizing analog objects that had an analog representation. Journals, that was a huge improvement. Think about how much time you would waste sitting in the library and looking for articles without a full text search, even for older articles. We digitized most of the scientific work of the past, like when libraries began since Gutenberg, or even before that, and made them accessible, so you can have full text search for all of things, so everything appears like there. But we improved it a bit further. We invented even a new class of digital objects, born digital objects. These objects don't have an analogous representation. They didn't exist before. They're purely digital, whatever that means. You cannot touch it, and if you switch it off, if you pull the plug, they're gone. It's data and data formats, but also software-based research. Most of this computational science is based on software, because some scientist took a lot of time of his time during his PhD to implement something, to implement a model, which is then tested with data. Do you know this guy? That's Vint Cerf. He invented the internet, not the World Wide Web. You must not confuse him with the World Wide Web. He invented IP. And he made a speech, I think, what was it? I can't find it, just recently. And he promised us that we are now entering a new digital dark age. The dark age was the medieval, because, yeah, you know, we had issues with believing and things. Now, we have this digital dark age, because we lose the records, we lose access to it. So, even if you cite the traditional way of citation, something. So the old or typical way of citing a website was putting the website in a footnote, and when you have last accessed it. But of what use is it? No one can actually tell how it looked in 15 years from now, even in 3 years, because the internet is progressing that fast, and it forgets we have the Internet Archive, but that's just a bit of it. It's not the deep view. It's not everything. It's a bit. So we need to do something. So research data management is required, as you heard previously. It is very much scientific and economic self-interest, because you need reproducible science. And I think what people also forget, there are hidden gems. You may be a commercial company right now, an industry company, and you might have ideas where your management says, no, this is too expensive, or the production cannot do this, and so on. This might be different in 10 years, because the production capabilities are different then. So it is important that you can have access to things that have been invented 10 or 15 years ago in a way that is usable. And you don't have to start from scratch again, even though you know the idea. So we need a citation system for this. We need to make also these digital objects referable. And if we are able to cite them, we need to preserve them. Because if they are not preserved, they are not accessible anymore, and then the citation is useless. Because that's what the library does for you. If you cite a book, if you cite a PhD, or if you cite an article, there is a library, even if it's the National Library or it's the Library of Congress or some other place that has the article. And eventually you can have it. For the born digital thing, there is no such thing yet. So we need to start thinking about it, and we need to start thinking about infrastructure. This is also a nice view on it, that it's not only the data. We currently produce a lot of data centers and store data. We pulled just last year from 29 public repositories all possible domains we could find, a lot, like 2 terabytes of files, just samples, and to see what is inside there. And we found at least 140 different file formats, and that is just the lower bound because that's how good the tool is detecting file formats. We cannot look in everything, and we are not expert in any of these domains. We have no idea what that is about, and it's maybe just a binary thing that we don't know what this is about. And the other thing is what we found, it's not about the number of different file formats. It's the number of different file formats found in a single data set. It's not, there are simple data sets like weather data or I don't know, which are easy parsable because they're just time series. But there are complex data sets which contains multiple formats which belong together to build something together. So even the humanities use an average of about 10 different file formats per data set. So in this case, you need 10 different programs to open it. So we need the software to open it. What are software objects? They're storage-based. They come with a file, are defined by a file format. That's what defines Word. It opens a Word and it allows you to modify it. It comes for a more complex file format, does the same. For a CAD program, you need AutoCAD in a certain version to open that file format. It has a permanent immutable state, so that it remains there even if the computer is not running anymore. And it requires hardware or an equivalent. There it comes with to execute it, to do something with it, because software needs to be executed. So we need to do two things. One is collection, and the other one is to maintain access to it. That's for the file formats. Because for the data, that's simple. We just put them on tape or whatever we have for storage. And the storage, I wouldn't say it's a solved problem, but we learn to deal with it. Here we still need to learn. There are a lot of software preservation initiatives going on. Currently, it's a very hot topic. So there is a Software Sustainability Institute, so they create software management plans, think about how to collect software in a structured way, how to deposit it, how to cite it, how to deal, so also preserve the source code if possible. And then there are some other initiatives like the Internet Archive, there's the UNESCO Persist programs, and a lot of smaller institutions doing all that. And we need the access. And emulation is one access strategy to do that. So we already talked about it as an abstraction, but now we need it as a tool. And you know, we already talked about it. You can simply implement, not simply, but you can implement it. Every hardware logic has an equivalent representation in software. That is what the computer scientist tells you. That's a pretty old principle. It's not a very new idea, but it's technically complex because you have to set up. So the usability is a huge problem. How to operate an old system? It's a really difficult problem. I mean, how many of you are able to use MS-DOS properly? And how many of you are able to connect, say, Windows 3.11 to the internet? I can tell you, it's not trivial. And without the Internet Archive, where you find really old manuals to do so, it's almost impossible. The second thing is the scalability. You can set up an emulator, do something like playing a game, but it has to scale. We have plenty of software items, we have plenty of operating systems, and we need simple access. And the third really, really difficult problem is the preservation paradox. We try to preserve something, or we preserve software with software which is contemporary, which itself is prone to the digital life cycle. Well, it's kind of not very intuitive. When we think about data, or data preservation, well, that's simple. So we need just to invent something more durable than tapes. So now we do DNA storage, or we do holographic storage, or put it into stone, or whatever. We find a way. But here we need the software. So we need to think about this. That thing, and that, so that's the 1879. And during that time, I can share the to get a better idea how this can be done, we need to take a look again on how a digital artifact works, how a digital object works, how a software object works. And also, again, we have layers. If you out of ideas, invent layers. So on the top, we have a huge number of digital object types, different file formats, infinite number of it. And every day we invent something new. But there is an upside. All the objects, especially if they come for citation or preservation purposes, they are fixed. What you cite in an article should be final, should be done. It must not change over time. That's a nice property. And then we have the lowest layer, that's the computers, the hardware equivalent. And the nice thing is, there is only a very small number of it. We have only a few numbers of architecture. So we discussed this with the virtualization and the emulation part. However, it requires continuous replacement, either because the hardware dies, or the hardware is just physically dying, or if it's hardware equivalent, like an emulator, it gets obsolete because the emulator is made for the current system, and the current system is dying, so you need a new emulator. So it needs constant replacement. Doesn't matter what kind of hardware equivalent you use. So do you remember this slide from the first, I think from the first session? So we have this instruction set ISA, and we have the operating set ISA. So that's somewhere in between. And that's where the virtualization works, that's where the emulation works, and this is also the place where we are working. Because that's the interesting part, because that's the connection between operating system, which connects to the hardware. And usually these technical interfaces are drivers or the instruction set. So every emulator has to implement, of course, the instruction set, and a number of hardware equivalents like peripherals, I/O devices, which are maintained by drivers. This is the place where we are, and this is also the place, without going into the full details, where we can solve the preservation paradox. Because now we have broken it down to the ISA. The ISA is documented. That's the manual Intel published, or ARM published. That is also final, it's changed. So the task is, if you invent a new type of a computer, someone has to sit down and just implement this ISA. That's not very, it's a bit of work, but it's doable. Especially, we will see the next slide, because of this. And the other thing is, if we are able to reduce the number of emulated hardware below and standardize that to a certain degree, everything that is up that technical interfaces, that can be kept working by just replacing the lower part. And this is where we put the split in, because we have many artifacts. We have some applications, we have customizations. That's all the user part, and then we have only these two tiny bits there, and that's where we can focus on. So how does it work? That's what you start with are base environments, what we call. Base environments represent a typical computer of a certain area. It's not necessary to have, I don't know, 1,000 of different Windows 98 computers. It's necessary that you have one genuine installation of Windows 98, which works with a defined set of hardware. And this is something you can build on. The next step is you create, starting with a genuine installation of an old Windows or MS-DOS or whatever operating system, you start to install software. But we do this in a very special way to make it scale. The software is are just derivatives, they're layers, like you know maybe from Docker or something. So ideally, there is only one genuine Windows 98 installation, or there is only one genuine Windows XP installation. That should be it. There are details. Languages are a huge problem, because in those days no one thought about why put every language into one operating system, so they created many of it, but it's a whole different story. But then you have one genuine installation, and then you put only a small layer. So that's what we call snapshots or derivative, which only contains the difference between the old system and you put on top. And you can what you get then in the end is kind of a tree. So you have a single root, and then from there on you have modifications of every flavor and every kind. And you can tap in every layer in between if you want to. That's based on block storage, so that's not very difficult technology, but it's very efficient. And it has another nice property. If you have to change, if you have to migrate from one emulator to another one, we only have to migrate one single system, the base system. All the other derivatives based on top, whatever has been installed on it, get this feature for free. And then we need to connect the object with it. So now we have a library of software installations, software available, software that is usable via emulation. And then you have a large repository of different data objects. And what you need is to connect these on the fly. This can be done with technical metadata. So it's what we call object environment. So you inject or associate an object referenced via DOI, for instance, from a data repository with a ready-made software environment. We can move this a bit further, also with containers, because containers work the same way. Containers are software. And as I told you previously, containers use the same technology, all use the same technology, but they come in different flavors. And then you have the software stack below, that's on the left-hand side there below, and that are the preservation risks. You need the container runtime, that's the Docker version. You need the Linux operating system, which implements the interfaces, and you need the hardware to run the Windows operating system. Ideally, on the top layer, you create a stable digital object by extracting the file system of the container and put into a defined format. Because all use the same technology, so you only need one runtime, and then there is a standardized runtime to do that. Because it's cited, it won't change anymore, so you don't need the convenience factor you had before. You can still have that, and you can still do the preservation also for that, but it doesn't scale that good. What you want are, or what we want are containers that contain a scientific method that is published in a paper, and that this becomes accessible for reproduction. And then you need only a few runtimes to run a huge number of containers out there, because all use the same standardized runtime. And that's not something we invented. That's there's the Open Container Initiative that does it, based on a kernel and using an emulator below that. So in the long run, the top is not changing anymore. It's the same as we saw in the previous slide. That's final, it's fixed, it's on tape. You need to build the container runtime once, and the only thing you have to replace then in the future is the hardware, or the hardware equivalent, by putting an emulator on top. And now I'm almost done. And with that, I want to leave you with a bit of a sadder story. So we all made this and achieved a bit of it. So we can make it, we can preserve software. We have a good intuition how to do that and how to keep what we have done until now accessible and citable. So we actually made the technology to a degree, or brought the technology to a degree that we actually can say we can achieve that. However, things are changing. I don't know if you know these two icons. Probably everyone knows the one on the right hand side. It's Instagram. on the left-hand side, there's also Instagram, but it was the old icon from the, I think, iPhone 3 era. And together with my colleague, there is a very interesting observation you can make. In the earlier days, the software had this 3D look. It made you the illusion that the software is something you can have, even though it's on a phone or something. It kept the illusion that it was like in the earlier days where you went to the shop and took a CD or a box with you. That was the earlier days of the iPhone. Now it went flat. This illusion is gone. They don't make this illusion anymore. It's not something you can have anymore. It's a service. The same you have here. Software isn't that easily accessible anymore. If you want to install the Internet Explorer, an old version of it, what you get and what you find is there are very small binaries that contain, they're only about a few hundred kilobytes. What they do is they start the installer and then they try to download things from the Microsoft server. Most of the things aren't there anymore. URLs have changed. Even worse, certificates don't work anymore. So the installation process is more or less broken. There are ways around it, but yes, but this is to illustrate the problem. So what I showed previously with the preservation, there are ways and initiatives that actually preserve software. Things that was sold on CD-ROMs. We can image CD-ROMs, make ISOs of it. We can image floppies and make ISOs of it, put it on tape, store it, create an emulator, also preserve the operating system, and rerun it. With the software as a service, and the new type and the new thing of software, the software objects became blurry. There are no more boundaries, or they are pretty hard to define. If you buy today Adobe Photoshop, you buy something, but it's not all of it, because there are many things you have that are what do they call in-app purchases. So you buy add-ons from a server, and that's not something you can easily keep forever. It's individualized. How to preserve a complex system like Twitter, or today, if you read the news today, it came with the MySpace. So someone found out that actually MySpace lost the music from 2000, about 10 years of music. There's no backup. And MySpace was important for the music industry in these days. Now, even today, it's even more complicated. There are an uncountable number of possible states, and there is a complex on-demand relationship between multiple systems. So if you switch on your computer, or if you start a program, a lot of things happen, and these things won't work if the computer is not connected to the network. Your game is not working if you're not connected to the network. The whole thing is very difficult to inspect, very difficult to capture, and very difficult to store. And there is less and less that remains on your physical device that you could image after we pulled the plug. And this is it's the end of my talk, to leave it this way. So we have a new type of obsolescence. This is the Google Cemetery. It's a very nice website that that created a graveyard of all the nice and Google services that have been around the past, I don't know how long is Google, I think 15 years or so, something. Most of them are gone. There are some nice and popular ones like Google+, the Google link shortener is gone, Picasa, and plenty of them. They're all gone. And the interesting part, and that was why we are thinking about it, is previously obsolescence was defined by technical means. So as long as you had the computer or the hardware, and as long as you had the media and kept the media working, you could use it to a certain degree, at least.
Dois.
Thank you. And now it's not technical anymore. Ooh. It became a non-technical decision when something is obsolete. I think I can finish without the microphone. I think it's easier to do that without a microphone. It's a management decision. And you want to pull the plug. So for us and for the future generation of researchers, if you want to keep your content. Thank you. Yeah, perfect. We have to rethink all this, and it's not that easy anymore just to emulate a machine or to preserve the CD-ROMs, but we have to invent a lot of new methodology. Previously we thought migrating an Excel sheet to a new version of Excel will solve the problem, or just print it. Then more complex objects came. Then we used emulation and virtualization to solve that problem. And now we have something like that. So if you haven't decided yet about your PhD, there are a lot of PhD opportunities in this field to think about how to deal with this problem. This is what we will see the next 5 to 10 years, and no one knows what comes after that. The good point is, however, we always have a bit of time. Currently, we are thinking about preserving and working with systems of the beginning of the internet. We have systems, we have solved the problem with working with older media like ISOs and floppies and simple software. Now my group is working to preserve connected servers, web servers containing of databases, complex software application servers, things that interact with each other, different groups of servers which are interconnected and interact with it, and specific clients. The next generation needs to deal with this thing. previously we had a lot of time because the obsolescence of the software and the media was rather long. Now, if you go to the website, you can see how long these services were active. The time frame is getting shorter and shorter. So we need more people in this field dealing with it, being aware of it, especially if you do research based on services like that, or with services like that. Make you aware what that means, if and how fast your research results, your research data, if it relies on such kind of services, how difficult it is to preserve them, and how dangerous it is that you will lose or that these things become inaccessible. So that's it for me. That was my module about computer abstraction and what we do with it in this research setting. We still have a few minutes. Do you have any questions? So we can make this a bit interactive for the last 5 minutes. No questions? All right, then I thank you very much. It was nice being here. I really enjoyed it. I hope you also took something out of this module, and I hope it will make this topic a bit more popular, because it is a very basic building block for our digital age and doing digital research. So thank you very much.